Hello, this is Math 2115 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled Quantification in Logic. There's a rule called universal insubstantiation, as it says here. It says if a property is true of everything in a set, then it's true of any particular thing in this set. Here's an example of it. If we say all men are mortal, and Socrates is a man, that forces Socrates to be mortal. It's similar to universal modus ponens. So if something makes P of x true, then it also makes Q of x true. So A makes P of x true, then A makes this. In the formal version, this would be for every x, if P of x, then Q of x, P of A for a particular A, then Q of A. So this is a statement that's similar, but we're using universal and existential quantifiers. So here's something for you to do. You want to rewrite the following argument using quantifiers, variables, and predicate symbols. And the question is it valid and why? You know what to do. Let's see how you did. So you would want to write for every x, if x is an even integer, then x squared is even. And if you think about that, that's of this form. For every x, if it's even, then the square is even. It is for this particular one, then it's true. So it has the form of universal modus ponens and is a valid argument. Here's another example using universal modus ponens. What conclusion can you draw using that? So if T is the right triangle with hypotenuse C and legs A and B, then C squared equals A squared plus B squared. The triangle at the right is a right triangle and both legs are equal to 1 and the hypotenuse C. What can you conclude? You know what to do. Let's see how you did. Well, the conclusion would be that C squared equal 1 squared plus 2 squared, which is going to be 1 plus 1, which is 2. And then if you wanted to know what C is, you would take the principal non-negative square root, and you would get the square root of 2 for that. Later on, we're going to prove that the square root of 2 is not a rational number. Here's the example of the use of the universal modus ponens in a proof. And so we need to know something that's happened here. So we need the definition of an even integer. So an even integer is even if and only if it is twice the sum of some other, twice the product, twice multiplied by some other integer. So that means something is x is even if x is equal to 2k, where k is an integer. So here's the theorem we're trying to prove. Suppose m and m are particular but arbitrarily chosen even integers. So m is equal to 2r for some r, and n is equal to 2s for some s. So we're trying to prove that the sum has to be even. That means m plus m, which is 2r plus 2s. Well, we can factor the 2 out, and so this is 2 times r plus s, and r plus s is an integer. So 2 times r plus s is even. Thus, this is even. Now, it's proved with a lot more granularity here, and in fact, I only did part of the proof, but this is the kind of proof I would expect you to do. And there are many examples in your book that I'm not going through, but I may ask you to prove something about numbers. So read the examples that are in your textbook as well as studying these videos. Another crucially important rule of inference is universal modus tollens. Remember that says if P then Q, not Q, therefore not P. And it works kind of the same way here, but you see we have the universal quantifiers. Here's something for you to draw a conclusion using universal modus tollens. So suppose I give you this argument. All professors are absent-minded. Tom Hutchinson is not absent-minded. What can you conclude? Write down an answer. You know what to do. Let's see how you did. And of course you can conclude that Tom Hutchinson is not a professor. Now, an argument is valid, and we define it here, means that no matter what particular predicates are substituted for the predicate symbols, the resulting premises are all true, then it forces the conclusion to be true. That's the same thing, except we're talking about quantified statements now. We say that argument is valid if and only its form is valid. But it's called sound if and only if its form is valid and its premises are true. So if I said something about, if Jim Bradley, being me, were 6 foot tall, then the moon would be made of green cheese. And then if I were to say Jim Bradley is over 6 feet tall, then that would mean the moon is made of green cheese. Well, that's a valid argument, but I'm not bigger than 6 feet tall, so that would not be a sound argument. We can use diagrams to test for validity. Consider this statement. I say all integers are rational numbers. We can represent that, and here's formally what you would say. For every integer n is a rational number. That means that all integers contained in here are rational numbers. And they are actually, because if you divide a number by 1, you're making it as a quotient. But you see, this represent that as a diagram. Let's use the diagram to show some validity. Suppose I say all human beings are mortal. Zeus is not mortal, therefore Zeus is not a human being. Well, you see, our first statement says, the major premises says that all human beings are mortal. That means the human being circle is inside the mortal circle. But Zeus is outside the mortal circle. That means he has to be outside the human being circle. And here's a picture of that. This is contained in that. Zeus is outside the outer circle. Therefore, we get this conclusion. So you see, the diagrams help us show validity. Here's another example, but this time we're showing invalidity. So here's the argument. All human beings are mortal. Felix is mortal. Therefore, Felix is a human being. Well, so we're saying all human beings are mortal, and Felix is inside mortal, but he may or may not be inside human beings. Here's an example where he is inside human beings. Here's an example where he is not. The conclusion, Felix is a human being, is true in the first case, but not in the second. He might be a cat. So because the conclusion does not necessarily follow from the premises, the argument is invalid. We also have quantified versions of you remember that if P then Q is not logically equivalent to if Q then P. So these informal statements have these formal realizations, and it's an error. This is called the error of the converse. Remember also that we said that if P then Q is not equivalent to if not P then not Q. That's the inverse. And so these are errors that people frequently make. And we'll talk more about that later, perhaps. This deals with an argument with no. So use diagrams to test whether this is valid or not. No polynomial functions have horizontal asymptotes. This function has a horizontal asymptote. Therefore, this function is not a polynomial. So use drawings to test this. You know what to do. Let's see how you did. And so here's the picture. So polynomial functions are over here, horizontal asymptotes over here, and this function is in this circle. So it's not the polynomial circle. There's also a version of the hypothetical syllogism or universal transitivity associated with this. So if the first implies the second and the second implies the third, that means the first implies the third. This means if P of x being true means Q of x is true, and Q of x being true means R of x being true, then that means that P of x is true. That makes R of x true. Here are the quantified versions of those statements, the formal versions of those statements. Now here, we're talking about evaluating an argument for Tarski's world. We're not giving you a picture though, we're just saying a bunch of things are true, we're just looking at logic. So what you're supposed to do is reorder and rewrite the premises to show that the conclusion follows as a valid consequence from the premises. So we say all the triangles are blue. If an object is to the right of all the squares, then it is above all the circles. If an object is not to the right of all squares, then it is not blue. Therefore, all triangles are above all circles. Give this a go. These are the kind of things we're going to be doing when we're doing proofs. You know what to do. Let's see how you did. Okay, so what we start out with is if it's a triangle, then it's blue. And if it's blue, then it's to the right of all squares. And if x is to the right of all squares, then x is above all the circles. If we look at 1 and 3, we can conclude that if it's a triangle, then it's to the right of all squares. And if we look at 4 together with statement 2 and use the transitivity, so therefore, if it's a triangle, then it is above all squares, or all circles, excuse me, which is the conclusion of the argument. Also, there's a theorem, and this is how you prove theorems as well with logic. We have a generalized De Morgan's law. If P is a propositional function, each pair of these are equivalent. And you see, if you negate a for every, you get there exists one that is not P of x. If you negate an existential, there exists an x such a P of x, yet for every x, it's not P of x. We're only going to prove A here, and there is an exercise, and you might want to try to do this yourself, proving part B. Okay, so suppose the proposition this is true. Then, for every x, P of x is false. That means that for every x, P of x is false precisely because P of x is false for at least one x in the domain of discourse. But if P of x is false for at least one x in the domain of discourse, not P is true for at least one x in the domain of discourse. So when not P of x is true for at least one x, then there exists an x, not P of x is true. Thus, this is true. The proposition then is true. Similarly, we could go through the argument for it being false, and we could prove that. This is the generalization of De Morgan's law for quantified logic statements. Just a couple of remarks on the converse and inverse. Let's suppose someone were to say, all the town criminals go to this bar. John goes to the bar, then he's one of the town criminals. Maybe he is, or maybe he's not, but that's some circumstantial evidence. The reason many people make this mistake of the converse and inverse errors is they assume that it is a biconditional. It's if and only if, rather than if John goes to, if you're a criminal, then you go to the bar. That doesn't mean if you go to the bar, you're a criminal, unless it's, but that's actually something that would be considered evidence, sometimes even for a scientific theory. And even in medicine, this is true. Let's suppose that a doctor was trying to make a medical diagnosis. Then it might be this. Oh, if X has pneumonia, then he has fever and chills, coughs deeply, and feels exceptionally tired and miserable. And you've got somebody who has all those symptoms. You might think, oh, they probably do have that disease, or they might have that disease. It is not a certainty. So the doctor might attempt to get further information, or they might try to start treating based on that. Now, many doctors are experts at doing this, and they have a lot of experience, and they make good conclusions. And this form of reasoning has been used in certain computer programs. It's called abduction. These are called expert systems that attempt to duplicate the functioning of an expert in some field of knowledge. And perhaps you've studied expert systems, and I know you're going to study artificial intelligence. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.